Hello, everyone, and thank you for joining us today. Welcome to Megger's monthly Testing Tactics webinar series. Today's topic is Directional Overcurrent Relaying Now and Then. My name is Greg Valdez, and I'm the Marketing and Communications Director for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NETA CTD and one PDH or 0.1 CEU for attending. You will receive this in an email within a week of this webinar. That email will also include a copy of the PowerPoint presentation and a link to a video recording of this webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. Our presenter today is Mohit Sharma, Megger Relay Applications Engineer. Also, to assist with the question and answer session, we will also have David Beard, another of our Relay Applications Engineers, and Danabal Mani. Okay, let's go ahead and get started. Thank you for joining us today, Mohit.
Thanks, Greg. Thanks for the introduction. So the title of today's presentation is Directional Overcurrent Relaying. I'm going to be covering about what we used to have back in the days in electromechanical world, what we have now, how we have progressed over the years, and foremost thing is why do we need a directional relaying scheme in our power system network? Why can't we just get over with the 51 element? Why there is a need for the 67? So all those questions that were there in your mind, I will try my best to answer those questions here in this webinar. At the end of during the final slides of the webinar, I'm going to also talk about testing because that's what primarily we do. I would cover some of the testing parameters, and I will just explain a bit of how to do the testing and what are we expecting out of that testing. And at the end of the day, I will conclude giving you a summary of what we covered. So let's get rolling. Start with the need for directional relaying. So here I have an example of a parallel feeder. You can see a generator on the left side. I have a load. I have two transmission lines, and in this case, I'm assuming the line impedance are exactly same, and the parameters of those lines are also matching exactly. So you have breakers A, breaker B, breaker C, and breaker D, and then they are protected by 51 overcurrent protection, which is your time delayed overcurrent. So in a nominal flow of the system, what you would see is you would see that the currents will flow through breaker A, B, C, and D to the load. Now keep in mind, since I talked about that the impedance are exactly the same of those transmission lines, I would have equal current flowing on my line between A and B and my line between C and D. So let's say there is a fault on the line between breaker A and breaker B. So what will happen? So in this single source model, my generator on the left is going to feed the fault through breaker A. It's going to go and feed the fault, but also since my breaker C, D, and B are closed, I would have a second path to my fault current, which would be from this transmission line 2. So what will happen? So if I have 51 element protection, as you know, it's going to trip after a time delay. So it always looks for the fault current value, and if the fault current value goes above the pickup of the relay is going to trip. So assuming that the coordination studies are done properly in this scenario, let's see what happens, which breaker will trip first. So the first breaker, since the fault is near to breaker B on transmission line A and B, I would have my breaker B and D tripped because the fault current is almost higher than the pickup. So after a time delay, I would trip B and D. And I have my breakers E, A, and C as my backup breakers. So if breaker B and D trips, I'm still feeding the fault through breaker A. You can see that on the blue line. So what's going to happen after a certain time delay, the backup protection will operate and it will trip breaker A. Now in this case, for a fault on line A to B, you're taking off the load. So the generator is not feeding the load. So how we can provide more reliability to my load, what kind of schemes we can implement. So 67 is one of the schemes that can be implemented in this scenario, which will allow some load to be there all the time, even though the fault is on any of the lines. So let's see what happens when I have 67. So 67 is actually is the ANSI standard for directional overcurrent protection, and 51 is nothing but non-directional overcurrent protection, right? So if I have a fault here, the directional overcurrent protection has a forward looking points and they have a reverse looking point. So for a fault happened on line A and B in this scenario, what will happen is my generator again is going to feed the fault through breaker A, and similarly it's going to feed the fault through the second transmission line from breaker C, D, and breaker B. So here you can see that I have my 51 element, this, and the direction for the 51 is in the same direction. I have a 67 element. So the current flow, the fault current flow is from the generator side to the load side. So you can see the yellow color, and then the black color here, the black arrow indicates the forward zone for the 67, or the operating direction for the 67 element. Now you see that here I have a reverse current flow. So what 67 does is it blocks the reverse direction from operation. So it will only operate the breaker if it sees a fault current higher than the pickup, and also in the direction it is meant to trip. But the breaker B, let's go back here. Let's say the breaker B here, the fault current is in the same direction as what the operate quantity is in. They are in line. They don't have any phase difference. So what's going to happen? My 67 meant to trip breaker B will trip breaker B. I'm going to trip breaker B now after a certain time delay, because I'm still feeding the fault through breaker A. I'm going to trip breaker A after some time, and this will be the case. So you can clearly see here in this case, I'm feeding the load, which is I'm feeding half the load, but I still have some load current. So for a transmission line fault, I'm not actually tripping off my load completely. So what does it tell me? It tells me that I have the 67 element can be a better scheme for some of the special distribution networks, like for your parallel feeders that we saw just now. It's also a better scheme for your looped network, which is also called as the ring networks, and for your multi-fed systems, meaning that you have more than one generation sources feeding a ring network or a parallel feeder. So in those cases, implementation of 67 has proven to be better compared with 51. As we see that it it increased the reliability to critical loads. So in your system, whenever the critical loads are present, it's always advisable to have 67 element protecting those critical loads. It's also more selective compared to the non-directional overcurrent that we saw in the example that I gave. And the other thing is, it also acts as a supervisory role for distance elements. Now, we all know that distance elements works on the principle of impedance calculation. So they have forward zones, they have reverse zones. So basically, the distance relay calculates the impedance, see if the fault is in the forward zone or is in the reverse zone, and it works on that principle. So I can have this directional element supervise my distance element, meaning if there is a reverse fault and my distance element is only looking in the forward direction, the 67 element will not give a permissive to your 21 to trip. So for a reverse fault, I will not trip, but the remote relay for the 21 remote relay might be able to see and trip it. So it also acts as a supervisory for distance. Now we understood why the need is required, why we need the directional relaying, but let's go into like in-depth fundamentals, how it is using the directions and how it is deciding whether the fault is in forward or the reverse side. So in any 67 element I have drawn here, it basically looks for both voltage phasors and current phasors. Keep in mind, it's not just looking for current, but also some kind of a voltage phasor as well. So it sees for voltage phasor and current phasor, and it runs some algorithms inside. If it's a microprocessor relay, if it's an electromechanical relay, it has some filters, and then it also checks for directionality. So the first thing 67 element does, it checks it checks for directionality. I'm sorry. It checks for directionality, right? So if if the directionality check says the fault to be in forward direction, it's going to give a permissive to 5051 element to trip. But if the directionality check is in the reverse direction and the element is not programmed to trip for reverse, it's going to send a blocking signal to 5051 and say that do not trip. So the 5051 element will not trip. So that's how this works. Now, how does it decide? So let's get into the concept of directionality check that I explained in the last slide. So here I've taken a multi-FET system example so that it's more clear. I have a 67 element here between breaker B and breaker C. So the CT placements are pretty important. You have to see where exactly the CT placements are and where the PTs are. So in this example, I've taken this is my CT measuring current for the 67 element. I have my PT on the bus here, and I'm measuring voltage for the 67 element. In this scenario, if I see a fault here between line C and D, I have a generating source G1 which sends the current in this direction, feeding the fault, and I have generated G2 sending the fault current in this direction, feeding the fault. So what would be seen by 67, since it is meant for the forward is meant for this in this direction, I would see a forward fault. And if I have the fault current higher than my pickup, I would declare, okay, I see a forward fault. Now it's up to 5051 to see what to do. You want to trip it after some time delay, or if you want to trip it instantly. It all depends on 5051 element after that. So, but the thing is, here you have to keep in mind that these transmission lines, they have some X by R ratio, meaning that they have some reactance over resistance ratio. It's not a pure resistive line. So my voltage would never be in line with my currents. So depending upon the fault, there would be some phase angle difference between my voltage and my current, right? So that's what I have shown here. And typically faults are lagging in nature. When I say faults are lagging in nature, it means that my fault current is lagging my voltage. Okay, so I have a fault current here, and I have some the phasors plotted here, and also it has been observed that if the fault goes away, the generating station, then there is a more lag in the go between the voltage and your fault current. So there is some kind of angle difference between fault current and the voltage, and we don't know that angle difference. It can be anything depending on what kind of fault you have, what feeder parameters you have. So it all depends on those parameters. But now we got the concept that, okay, I have my fault current lagging my voltage. So in some cases, faults can be leading in nature as well. So the fault current that you see here can be plotted here too. So what happens when I see a fault in the reverse direction? So let's say this example where the fault is in the reverse direction for 67. So in this example, you can see that generator G2 is feeding the fault, and the CT that is meant for measuring the current in 67 sees it in opposite direction. So it's a reverse zone for 67 in this example. So what happens? The fault current was reversed, meaning that it took a 180-degree shift out. So my voltage over here, I had my current here in the previous slide where the fault was between transmission line C and D. When I have a fault between transmission line A and B, there is a 180-degree flip that you can see here. Okay, now let's go and see what directional characteristics are and how we can define a characteristic in a relay. So as I explained to you that this directional relay works on the principle of voltage phasor and current phasor. But the way it operates is traditionally it operates on torque, right? So the voltage phasor and the current phasor interact with each other. There is a development of torque, and based on whether it's in forward side or reverse side, it's going to trip or restrain, right? So the here in this example, I have a signal which is called as a polarizing quantity. So this polarizing quantity is nothing but it's a reference quantity which is not affected by the fault. So it's unaffected by the fault. It's constant. So we can have this voltage polarizing as a good reference to decide whether my fault is forward or reverse. So I have decided my voltage polarizing here. In this example, my fault current is somewhere here. And then there is something called as the maximum torque angle in the directional world. It is nothing but it tells you that whenever you have a fault phase difference equal to your maximum torque angle setting in the relay, my relay would see a maximum torque. So the whole idea of maximum torque is faster the movement in the electromechanical world. So I would see a maximum torque on my disk. That's what it decides. And this maximum torque is very important in deciding the characteristics, right? So once you have this maximum torque here, then what relay design, the relay manufacturers do is they have like some kind of a blinder. So in this example, I've taken a plus minus 90 blinder. So if I see my fault anywhere in this gray region, I would declare that as a forward fault. No matter if it's leading a bit, because faults can be leading in nature. So I have decided this line as my partition line between the forward and the reverse fault, and this partition line is called as the zero torque line, right? So the zero torque line decides where the forward area is and where the reverse area is. MTA is also referred as relay characteristic angle or the Z1 mag in some relays. Now let's take a look at the quadrature polarization. So the idea of quadrature polarization is decided from your phase triangle relationship. So you have your phase triangle I've plotted here. So I have my voltage phase A, I have my voltage phase B, voltage phase C, and then phase-to-phase voltages or line-to-line voltages. So this is my plot. So what quadrature polarization tells me that if I have a phase fault, I'm going to have BC voltage line to line as my reference, because BC voltage is not affected by a phase fault, right? So this is a very good design used in many of the relays, in many of the directional relays, where they basically have sense for the other phases for voltage and keep that as a reference. Now, why do we call that as quadrature? Quadrature is nothing but 1 by 4, right? So in the reference plane, you have 360 degrees multiplied by 1 by 4. So you have 90 degrees. So this is nothing but a 90-degree connection, right? So what exactly is 90-degree connection? So the 90-degree angle is between your phase A voltage and the polarizing voltage. You see, I have a 90 degree between my line to line voltage and line to neutral voltage. So I would use VBC as my reference whenever I see a phase A fault. I would use VCA as reference whenever I see a phase B fault. And I would use VAB as my reference whenever I see a phase C fault. So this whole idea of quadrature polarization is employed primarily in phase directional relaying. So phase directional relays are typically implemented and are there in the system to protect against three-phase and phase-to-phase faults. So as I explained to you that VBC is kept as a reference phasor for any fault if you have the fault is on the A side. So A phase fault, you have VBC as reference. So that's what it is talking about here. And we saw that why it is called as 90-degree connection. So in this example, the maximum torque is set at 60-degree lag, meaning that my angle here is lagging my polarizing quantity by 60 degrees. That's the maximum torque angle. And based on the maximum torque angle, I can define my forward and reverse zones. So let's now take a look at the connections. So how the connections are there in the field. So I have a station bus here. I have some CTs. I have three-phase CTs going into this breaker, and then I have open delta connection for sensing my voltage. That's my PT. And this is open delta or B phase grounded. And this is a low voltage line, and I'm basically measuring voltages from here. So you see that the phase connections for any directional relay, it's going to measure phase currents, right? The currents would be from the phase CTs. And what about the voltages? So I explained to you that if it's a phase A fault, I have to sense for B and C voltage line to line. Keep in mind that's line to line. So for phase A, my connections would be B to C, right? For phase B, it's going to be this one, and for phase C, it's going to be this one, right? So we see that this is how the connections we would be making it in the field. Now let's go to the ground directional relaying. What is ground directional relaying? So now we know that ground directional relaying looks for any current flowing in the ground circuit. So we know from symmetrical component theory that that's a zero sequence current that flows through the neutral of a Y-connected circuit. So you basically use in ground directional relaying your zero sequence voltage or your zero sequence current as your reference, depending on what kind of you have, what kind of power transformer connections you have. There are many other factors that decide whether you want to keep zero sequence voltage or zero sequence current as a reference phasor. But how do we get the zero sequence voltage in electromechanical relays? We don't have any kind of calculator or any kind of mathematical tool inside those relays to basically measure zero sequence voltage. So they measure zero sequence voltage by the way we connect the voltage transformer, by the way we connect PTs. So we're going to see the connection called as broken delta. And by this broken delta connection, zero sequence voltages can be computed. And in microprocessor relays calculate zero sequence inside their box. And then if you're using a zero sequence current for polarization, it can come from your transformer neutral CT or a core balance CT. So it can come from there. And the operate quantity in ground directional relaying is nothing but your residual current from phase CT connections. So this relay is basically nothing but looking for any kind of angle between zero sequence voltage and zero sequence current. So let's see the connections here for the voltage polarization for ground. I have my CTs here, and then this goes to the phase 67P element, and then they would be summed up here at the neutral point, and then the zero sequence current flows, the neutral current flows here, which is being measured by the 67N. So that is called as the residual current, and it is 67N is taking that as the operate quantity. Now, for the polarizing quantity, I said that it takes broken delta connection. So here is how I've drawn a broken delta. You can see that the non-polarity end of phase A connected to the polarity end of phase B, and non-polarity of phase B connected to polarity of phase C, and non-polarity of phase C is open-ended. It's going directly to your 67 and neutral voltage for voltage measurements. So that's the reason it's called as broken delta, because I'm not connecting the non-polarity of phase C back to the polarity of phase A. So when you do this, this guy right here is nothing but it's computing from the Kirchhoff's voltage law. You would see that it computes nothing but phase A voltage plus phase B voltage plus phase C voltage. So if you remember the symmetrical component theory, phase A voltage plus phase B voltage plus phase C voltage is what? It's either 3 times zero sequence voltage, correct? So that's where we are measuring zero sequence voltage from in the world of electromechanical relays. Even microprocessor relays employ this concept, but we'll see later. Now let's take a look at the electromechanical world, what all relays we have, how basically their operation is there, and the other things. So I've taken here an example of a phase directional ABB CR relay. In the right side, you see the picture. In the picture, they have an induction cylinder type unit. That's actually the directional unit. And then they have the directional unit is induction cup type, and then you have a time overcurrent unit sitting just below the induction cup type unit, which is the induction disk type unit. That's your 51 unit, and that's your 67 unit. That's your directional check unit. So this ABB-CR relay, since it's an electromechanical relay, it's a single phase relay, so you need all the 3 relays connected in your system. You need 3 relays to protect your 3-phase system. So you need similar relays. The problem, I wouldn't say that is a problem, but the thing about MTA with this relays is there is no setting for the MTA on the nameplate or anywhere on the tabs here. So the way this relay decides MTA is by the connections that has been made inside the relay. So in this relay, it's a fixed MTA relay again, and specifically this ABB-CR is a 30-degree current leading voltage relay. So there are not many MTA options available in electromechanical relays. So now let's talk about this induction cup type unit, which is the directional unit. This has diametrically opposite winding coils. One coil for your operate quantity, one coil for your 2 coils for your operate quantity, 2 coils for your restraint quantity. So the operate quantity is in phase directional would be what? The phase currents, right? So that's going to be operating on phase currents, and the restraint quantity the polarization quantity would be measured from your quadrature connections, the 90-degree connections. So the operation of this induction cup type is it looks for torque between the operate quantity and the polarizing quantity and see if the torque is higher. If it's higher than the required, then it's gonna just close the contact. Once the contact is closed, now my DOC is good for tripping, right? So this is employed because this induction cup type are having low rotor inertia and high torque, so they provide high speed and sensitivity. Um, Here is a schematic of this ABB-CR relay. You can see that if I have studs 8 and 9, and basically the current is going to be coming on studs 8 and 9. You have an instantaneous coil, you have a time over current coil, and a directional coil all in series. So this directional coil is the operating coil. And then on 6 and 7, voltages would be coming up, and this is your polarizing coil. So you see in the contact here, if the directional check is okay and directional check tells that it's a forward fault, then this D contact is going to close, and then I can close my CO contact is ready to close after that. Let's take example of now for a ground directional electromechanical relay. GE JBCG is one of the ground directional relays. It provides protection against phase to ground faults. You can see that there are 3 different units in this box. The bottom one is actually the directional unit, exactly like what we had in the ABB-CR relay. And then they have a TOC unit, which is the time over current unit, and then they have an instantaneous unit right here in this particular relay. But the thing about this ground directional relay, the whole idea about this directional unit is it can have dual polarization options, meaning that I can either choose a zero sequence current as my polarizing quantity for this unit, or I can choose zero sequence voltage for polarizing quantity. So it gives you an option of choosing any one of them depending on your system parameters. Sometimes zero sequence current polarization is better, sometimes zero sequence voltage is better. So here is the connection drawing for GE JBCG relay. If it says that if potential polarization, the zero sequence polarization is used, you basically connect A to D and you connect B to C. So this is nothing but a broken delta PT. If you are using a current polarization, zero sequence current polarization for this relay, then you have to connect it from stud 7 and 8. And the stud 7 and 8 are basically taking it from the transformer neutral CT. So depending on what you want to select, you can choose one of them. Now let's see what is there in the microprocessor world. So microprocessor world, we have implemented a lot of digital processors inside the box. They have a lot of algorithms going on in the box itself. So here is I just draw a very basic drawing of what it's there in the digital relay. So this digital relay is measuring phase A voltage, phase B voltage, phase C voltage, phasors. Similarly, it measures the phasors, phase A current, phase B current, and phase C current from the inputs. So the relay has 3 phase inputs for voltage and current. It's going to measure voltage and current from PT and CTs. And what it does inside the relay is it basically disintegrates those phasor quantities into sequence quantities. So in the calculations in the box, it does positive sequence voltage, a positive sequence current, and similarly it computes negative sequence voltage and negative sequence current, similarly zero sequence quantities. So once it computes all those quantities, and based on those quantities, it decides whether my direction is positive or whether my direction is forward or reverse. And then it gives a permissive to 50-51, and the 50-51 is then waiting either for some time delay or it's going to go for instantaneous trip. So we have seen that. Let me take you back here. We've seen that phase relays use quadrature polarization traditionally, and ground relays use zero sequence polarization traditionally, right? So, but in microprocessor relay, you have the freedom to choose whatever polarization signal you want to use, since you have all these quantities. You have your positive sequence voltage, you have your positive sequence current, you have negative sequence, you have zero sequence, you have everything inside the box. So not some actually, most of the relay manufacturers also have negative sequence directional relay. So you can implement uh, that that method as well in the relay. So everybody knows that negative sequence are primarily present when you have a phase-to-phase fault or a phase-to-neutral fault, phase-to-ground fault. So in those cases, I have pretty good magnitude of negative sequence quantities in my system, right? So I can use those negative sequence components, since negative sequence component are more sensitive compared with the phase sequence, the phasor values. So in some cases, this negative sequence directional element can be implemented. So the key thing here is, in case of a fault condition that I explained, it's a phase-to-phase fault or a phase-to-neutral fault. These negative sequence values are present in relatively high numbers. So you can set at a value, you can set your elements at a lower value, ensuring sensitivity. These negative sequence elements are also load independent. So if the load is changing, negative sequence element is independent of that. Sometimes, in some of the special cases, like when you have mutually coupled lines with different zero sequence polarization sources, in those special circumstances, this negative sequence directional element has proven its worth for ground faults compared with the ground directional element. So sometimes it's better than ground directional as well. The way it works is it basically looks for the negative sequence voltage as the polarizing quantity. So that's my reference. And it looks for an angle between negative sequence voltage and negative sequence current. So this negative sequence current is going to generate whenever you have a fault, right? So it looks for the angle between both these quantities. And if the angle is falling in this region somewhere, I would declare as a reverse fault. If it is falling in this region, I would declare that as a forward fault. Now see that I have little difference here in my phase quantities and phase directional elements. You have seen that the current lagging typically was kept as a forward direction, and the current leading was kept as a reverse direction. But this is negative sequence, so this is just the opposite of your phase quantities. So if your system rotation is ABC, negative sequence is rotating in ACB direction. So it's just the reverse of your phasor rotation, the system rotation. So the forward fault is declared in this case when my negative sequence actually leads my negative sequence voltage by 180 minus the maximum torque angle. 180 is nothing but this is when you have plus minus 90-degree blinders. So that's what it is. 90 plus 90, 180 minus the maximum torque angle. If it's leading by this angle, then I can declare that as forward fault. So let's take a look here in how microprocessor relays are different from electromechanical relays when directional elements are concerned. So in microprocessor relays, since I told you that they have phase inputs and they also have sometimes an auxiliary input. So your zero sequence voltage can be calculated inside the box by measuring the phasor quantities from the phase inputs. So V0 can be calculated from three-phase PT inputs. or V0 can be used as the fourth auxiliary input on relay. So, and that fourth auxiliary input you can connect either to the broken delta PT connection, or you can, for the voltage zero sequence voltage polarization method, or you can connect to a neutral of an impedance grounded generator or transformer if you are using a current zero sequence current polarization technique. Similarly, for your zero sequence current can be calculated from your three-phase CT inputs, which are there. So the relay can calculate the zero sequence quantities inside the box, or sometimes they have a fourth auxiliary CT input, just like the PT input on relays, where you can use that special, like one input to look for zero sequence current measurement. So that that fourth auxiliary CT input can be connected either to your flux summing CTs or core balance CTs. Core balance CTs are nothing but they are basically measuring the zero sequence current. And then also, if you are using, this is when you use zero sequence current method, and you also can connect the fourth auxiliary CT input directly from your transformer neutral if there is a CT present on your transformer neutral. So you can directly connect that one to the fourth auxiliary CT input, and that's going to measure the zero sequence current. So I can have that as well as my connections. So I have the freedom in microprocessor relay to either calculate zero sequence quantities or directly use based on the connections in the system. But in electromechanical relays, if you remember, it doesn't calculate sequence quantities. All it can do is you have to connect your PT in a certain fashion to measure the zero sequence. Now let's take a quick look at testing of directional elements. So the electromechanical directional elements in relays, electromechanical relays, we saw that there is a separate directional unit, there is an overcurrent unit, and there is also sometimes an instantaneous unit. So in the testing world, you would be testing the minimum pickup on your directional unit. It needs to see some VA to basically trigger the induction cup contact. Also, in the directional unit, an MTA test can be done and to see whether the induction cup contact basically operates for forward or it operates for reverse. So you can check that from the maximum torque angle test. Overcurrent is the straightforward minimum pickup test. Overcurrent unit timing test is basically making sure that the relay trips for the time curve that it is meant for, or that it is set for. And then you have instantaneous unit. Sometimes they have seal-in units as well on those relays, so you can check those seal-in by injecting DC current onto that and see whether they are operating or not. So in order for you to operate a directional unit and test a minimum pickup on that, it all depends on different manufacturers. So they provide you that information on the nameplate. You can check the nameplate and see what the minimum pickup is, and then you can inject your currents accordingly. This CG relay in particular, when it is voltage polarized, the minimum pickup at the maximum torque angle is you can set anywhere from 3.6 to 14.4 VA. So remember I said that directional unit pickups are always in VA, volt amps. This relay, when current polarized, minimum pickup can be settable anywhere between 0.25 to 1 amp. So whenever you're using voltage polarizing elements, keep in mind your pickup would be in units of voltage times amps. Now let's take a look at the microprocessor relay. I have one relay here. I have some settings on the relay. You can see that the maximum torque angle setting on this relay is 60-degree lead, meaning that my current is leading my polarizing quantity by 60 degrees. It also has the minimum polarizing voltage setting, 0.05 times the secondary voltage value of your potential transformer. And it also has some relays that it tells whether to operate or not. So relay 4 is in operation at the moment. So this is the phase directional settings in this relay. In this relay, the nominal voltage of secondary was 69. So 0.25 times 69 would mean 3.45 volts. So I have to inject at least 3.45 volts to polarize my relay. The reason for having some minimum polarizing voltage is, let's say you have a three-phase close-in fault. So if it's a three-phase close-in solidly grounded, three-phase close-in fault, my voltages will collapse to zero. So the voltages collapse to zero. When in that case, when the voltage collapses to zero, there is no reference. So how does a directional relay decides how to trip if there is no reference at all? So in microprocessor relays, what they have is they use something called as memory voltage. So that memory voltage is looking for a pre-fault vector that was there stored in the memory just before the fault happened, and it uses that pre-fault vector as the reference quantity in the after the fault. So you use that pre-fault vector, voltage vector, as a reference, and then you can basically trip on directional three-phase elements as well, even on three-phase close-in faults. This relay has a setting called as block overcurrent when voltage memory expires, and it is set for disabled. So it meaning that when that voltage memory concept that I explained, if that expires, do you want to block overcurrent or you don't want to block overcurrent? In this one, it says don't block overcurrent, meaning that if my voltage memory expires and I'm able to see some voltage, I would like, and I'm able to see the directional check to be in the forward direction, I would declare that, okay, 5051 element, now you are good to go and you can trip. If it is set for enabled, 5051 will never get a permissive to trip. So that's what it is. This is the time overcurrent setting of that relay as 1.25 times the CT, secondary CT nominal as the pickup point. So 1.25 times CT is my pickup, and then the time dial on this relay is 10, and it's following a very inverse time overcurrent curve. And the directionality for operation is actually in this relay, it is set in phase time overcurrent settings. So the directionality for operation is forward, meaning that I would operate, the relay would operate the time overcurrent element when it sees the fault is in forward direction. So even this setting is quite important to see when that directional element's gonna block the overcurrent and when it's gonna allow the overcurrent to trip. I really apologize for this VPN gateway thing. And then the other test is called as the maximum torque angle test. This maximum torque angle test is basically looking for, it's testing the maximum torque angle setting in the relay and ensuring that the setting in the relay is expected to be right. So the way to do this maximum torque angle test is you provide currents higher than the pickup setting on the current magnitude, and you provide the voltage magnitude you can keep as a balanced voltage and have the magnitude of the voltage higher than the minimum polarizing voltage magnitude, which was 3.45 volt in our example. So if you keep a voltage higher than that value, my relay is polarized, and if my current is kept at a value higher than the pickup setting, I can go for trip, but only in the case when my angles are in the forward zone or in the forward side of the characteristics, right? So this test is doing nothing but it's changing the phase angles to see at what point it trips and at what point it's blocking the relay. You can see here the characteristic here, this yellow line in this example is actually the zero torque line. And then this blue shaded region is the operate region. So in the maximum torque angle, basically you start from a point here, somewhere outside your operating region, and you increase the phase angles or decrease the phase angles depending on what kind of rotation you have, and you change the phase angles and you wait till that quantity that fault quantity goes inside this characteristic. Once it is inside this characteristic, it's going to trip instantly. So, and I can record that phase angle value, and I can say that, okay, I can compute based on the blinders, I can compute whether that setting is actually matching my maximum torque angle setting or not. So in this example, you see that my setting was 60 degree in the relay, and I actually got an MTA of 57.4 to 57.3 and 60 degree on three-phase element. This is running a phase directional test, and remember, phase directional in most of the circumstances is the quadrature polarization method, right? So the directional overcurrent pickup test, the way to do in microprocessor relays is you provide the phase difference between your injected currents and voltages exactly at the maximum torque angle, and you provide a value of balanced voltages higher than the minimum polarizing voltage magnitude, and then you basically increase the currents and wait for when that time overcurrent element trips. So here I use the 51P element and not the 51P element. So you're basically measuring the pickups, not the timing. You can also do a timing, which I have not shown in the slide here. And to conclude the webinar, phase, I've covered the differences between phase directional connections and ground directional connections. We have seen that directional relay works on the principle of polarization. We have also seen directional relays provide better selectivity, speed, and security, especially in some two-source and ring networks. Both current and voltage phasors are required. Keep in mind, this traditional directional relays are working on the concept of phasors. So you need to have both current phasor and voltage phasor in order to simulate a trip condition during testing. And the key point, takeaway note from this webinar should be that every relay manufacturer is different in defining their phase angles. So it's always advisable to go into the instruction manual of the relay or get in touch with a relay expert to see how the relay has defined the zero torque line, basically. So how they have defined what side is characteristic forward, what side is characteristic reverse. In the webinar, I have kept plus minus 90 as my blinders. Some relays also have, you can set the blinders in those relays. You can keep it like at plus minus 60 or any other number. So it's always advisable to check with the relay expert or check in the instruction manual to see how the characteristic is defined. Once you know the characteristic, then you can test directional elements easily. Now, I would conclude it. We have some products that you can use to test directional elements. We have SMRT 410 unit that has 10 current channels and has 4 voltage channels. So you can use either this one for your 67 element testing, or you can also use, we have a 46D unit that has the onboard display onto it, and the software on the onboard display is exactly the same software that you get on the PC. So it's you can program the directional element trips on the onboard display itself. This unit has a maximum of 6 current channels and 4 voltage channels. So I have my 3 voltages and 3 currents that I need to test my directional elements. I can get it from this box or even this unit. The good thing about the D units that we have is whenever you connect the D units with the PC, so the PC takes the control, the software in the PC takes the control, and the onboard display turns it into a meter. So you can actually check the metered outputs from your current and voltage. It's always a good practice to see what values the test set is outputting, the magnitude of current, the phase angles. Once you know that, it becomes really easy to troubleshoot some of the testing dilemmas. We also manufacture a single phase unit that is called as SMRT1. This SMRT1 has one current channel and one voltage channel that can be converted to a current channel. So you can use this guy to test electromechanical directional relays, phase relays. You can have the multiple units, stack them. You can stack them into different numbers. You can daisy chain them basically and have more than one unit as well. So these are our product line, and I would now hand over the webinar to Craig.
Thank you, Mohit. At this time, the presentation portion of the webinar is officially concluded. Now we'll take about 30 minutes to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that might be leaving, when you close the webinar window, a survey will pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there is a field where you can also request a demo or quote on any Megger products. Again, a copy of this presentation, along with the link to the video recording of the webinar, will be emailed out to everyone in about a week. You can also view recorded webinars from previous webinars on our website at us.megger.com/webinars and register for next month's webinar, PD Testing in the Life Management of a Cable. That presenter will be Robert Probst, another one of our Megger Cable Products managers. Now let's get to your questions. First one we have on the list is, on a high resistance grounded system, the capacitance current is the design factor it flows from line to ground and balance. But during a single line to ground fault on the network, this capacitance current changes its direction and flows from ground to line because the total current now is the vector addition of NGR current plus this reverse gap current. Is there any way that we can have ground directional protection 67N using a zero sequence CT?
Hey, this is Dhanapal here. For this question, yes, the answer is yes. We can able to have a directional element with a 67N with zero sequence current. Probably we may need the zero sequence voltage measurement circuit in the NGR circuit. On the generator grounding side or anywhere you've got a high resistance grounding, you might need to have a zero sequence voltage measurement option. Then if you got that one, you can implement 67N element for this kind of application. Go on.
All right, excellent. Our next question is going to be on slide 10, the fault between A and B. How will BKR B and D trip first?
Yeah, I can take this one. B and D also like the fault current will be fed for that particular location is from through C, D also, because the current is also coming in other directions. Since the picture shows all 51 elements, so it is non-directional element. B and D can also operate.
All right, next question. Does the fault current always lag voltage? If so, why? Mohit, can you take that one?
Yes, I can take that one. So it is not necessary that the fault current will lag the voltage when you have high capacitance on your transmission line, meaning that your capacitive inductance is higher than the inductive reactance. Capacitive reactance is higher than the inductive reactance. You can have fault current leading the voltage. So there are some cases where you can also have faults where the current is leading the voltage.
Okay. What are the typical applications for directional overcurrent relays? Mohit, if you can answer that one as well.
So the typical applications of directional overcurrent relays, as I explained in my slides, that you can use that application. You can use those relays for protection in your loop networks, and when you have parallel feeders. So that if you use those elements, then your reliability in the power system network is improved. Instead of using the 51 element, I can use 67 to have more reliability. So the application would be you have a phase fault on a parallel feeder that I showed you in my slide. Let me go back here. Let me go back to my slides. Like in this case, in this example that I showed, this kind of an example, your 51 element might trip both the breakers on the bus, and the generator is not even feeding the load. So, and if I use 67 in this scheme, I can get half the current that I'm supposed to fed to the load. So there are some special cases where directional element proves its worth compared with the non-directional element.
All right, next question. Based on your experience, have you seen directional overcurrent elements applied on series compensated lines to trip or supervise operation? And any risk of misoperation if applied? Danabal, if you can answer that one.
Yes, this is one of the great questions I have seen. The question is, yes, we can apply the directional function in series compensator line, but the risk is very high. We have to do compensation properly. It's not like other method like we use positive sequence or zero sequence stuff. On the series compensator lines, you got a MOVs present across the capacitor along with the compensating reactors. In case of high fault current, the capacitor gets started. In case of low fault current, the MOVs are like very much conductive. So what happens? The production will mal operate. Also, one more issue on the series compensator line. It is a sub-synchronous frequency component. It is like a switching frequency vary from 5 to 20 hertz on this transmission line with a series compensation. This will cause the phase comparator to mal operate on the directional element. So what relay manufacturer does to compensate, they really do add the impedance biasing method. So they use offset impedance method on directional overcurrent element to compensate to bias the ground overcurrent elements misoperation.
Okay. Next question is for Mohit. In the torque equation, K times
voltage polarized,
etc. What does the K stand for? Thanks.
It's just a deciding. It's just a factor. Let me just go back there. I think it was somewhere here. It was, I think, in the fundamentals track. Yeah, let me just give me a second. Let me go to that equation. Yeah, there you go. Yeah, so this K factor is nothing but it's just a factor introduced to basically look for the calculations. You have to know the voltage polarizing quantity multiplied by your fault current times your cosine of phi. You always have this torque. This is called as a restraining factor, the torque restraining factor, and it is dependent on the coils that are used in the directional relays. So you remember I talked about the directional unit in electromechanical relays. So they have coils for your polarizing signal sensing and for your current operating signal sensing. This K is nothing but a restraining factor for those coils.
All right. Next question, Mohit. How is B-pole ascertained and maintained?
Can you repeat that question, please, Greg?
How is the V-pole ascertained and maintained?
V4, you said? I couldn't hear you, sorry.
Oh, it's like the question is how polarizing voltage is ascertained and maintained in the directional element.
Certainly.
Okay, I can take this one. The polarizing voltage is generated. It depends on zero sequence polarizing voltage or negative sequence polarizing voltage. In case of the fault, the system voltage collapse. If it is a zero sequence element, it get enabled and we see numerical relays can see the polarizing voltage all the time. In case of electromechanical relays, the disk get closed, and that's how the current circuit get closed. So two different way, numerical relays and electromechanical relay work. It get outside when there is a fall. Yes, is a collapsing voltage.
Mohit, on slide 21, someone was asking, are the phase-to-phase vectors pointing in the right direction on your diagram?
Yeah, I'm on.
Sorry, what was that?
Yeah, can you repeat the question again, Greg? I'm having a hard time listening.
Yeah. Sorry, it was on slide 21. Someone was asking about the phase-to-phase vectors and if they're pointing in the correct directions. And if so, can you explain how your diagram is kind of set up?
Can you please?
Yeah, I use this diagram just to explain. I kept a BC voltage value on the zero line, and based on I'm using only this one as my reference. So the whole idea for showing this slide was that VBC is acting as a reference. So whatever angle VBC is at, the angle for the fault A current would be just based on that value. So I try to keep it simple, just to show that voltage BC is kept as a polarizing quantity and it's at 0 degree reference.
All right. The next question is for Danabal. Can leading power factor currents, especially at low power factors, spoof directionality?
It's a good question too. It depends actually when the directional elements are used in the generator production. The possibility of mal-operation is there. So we use reverse power functionalities to avoid this leading direction element operation. But it is possible sometime in the generator production relays. But in line production, no, it's not.
All right, Mohit. Next question is: could you explain broken delta a little bit more?
Let me go back to that slide. It's not here. But here. Let me check it out. Where exactly is that? Yeah, the broken delta is, you see that the connections here, I have my PT connected in open delta fashion from station bus to the low voltage bus, and then this is B phase grounded, and then from low voltage bus, this is how my PTs is connected. The primary side of the PT is Y connected, but the secondary side is connected in this connection is called as open delta. So this is my phase A, this is my phase B, and this right here is my phase C. So A is connected to polarity of phase B, and then non-polarity of phase B connected to polarity of phase C, and then non-polarity of phase C is actually grounded, and it also taking this voltage and this voltage. So if you apply Kirchhoff's voltage law, you would see that the voltage across your 67N element would be nothing but a summation of phase A voltage plus phase B voltage plus phase C voltage. So when you sum them together, VA plus VB plus VC is nothing but 3 times V0, which is your zero sequence current. So that's how electromechanical relays have studs connected here. So you can connect your PT in this fashion, and you can have those polarity on phase A going to stud on this side, and non-polarity on phase C going to stud on this side. So these two studs are measuring the voltage, and let me show you here in the electromechanical example. So 6 is polarity and 7 is non-polarity. So this is the phase A polarity, and 7 is the phase C non-polarity. So you can see that summation would be your zero sequence voltage, and that zero sequence voltage is being used for polarization.
All right. Thank you, Mohit. The next question is for Danabal.
Mohit.
Could you please go to slide number 22, Mohit?
Yeah.
On your presentation? This next question pertains to slide 22. So the question is, could you please explain how zero sequence voltage and current can be provided by the fourth auxiliary PT if the primary PTs are connected in delta configuration?
Yes, we can have a secondary connected in the open delta because the PTs are having multiple cores on the secondary. We can use one setup core for having the phase elements, another setup core we can connect in the open delta PT, then we can get the fourth PT for the directional element input. Yes.
All right. Next question is for Danabal as well. Does memory voltage change? It should monitor the voltage prior to fault so as to provide a reference. Is the memory reading and storing the voltage like, say, every 5 minutes or so, or how does it work?
Yes, memory voltage change. There are two different type of relays in the market, like electromechanical relays and numerical relays. In case of electromechanical relays, we use the relay manufacturer use the capacitor inside to keep the last operated voltage as a memory voltage. That get changed every time your voltage in the power system changes, where the relay is connected. In the modern numerical relays, that can change easily, means that last fault, whatever it is recorded last fault, that is the memory voltage. That can also get changed, but it never changes every time. Like when there is a transition of fault, then it gets changed. Yeah, it's not like minutes or hour.
Okay. Next question is it possible for the end user to change the blinders that was preset by the manufacturer, or is it set and unchangeable?
Yes, it is possible to change in case of numerical production relays, because the modern relays have a capability to change the blinder settings, but in case of electromechanical relays, no, it is fixed. It's based on the coil design.
All right. Next question, on the different polarization options, which is the one you recommend? Positive, negative, or zero sequence, supposing you have all options available?
It's like very open question. I can say it depends actually. The positive, negative, zero sequence selection depends on the application where you are using actually. Next one.
Okay. Next question. When performing in-service measurements on a directional relay with quadrature connection, would it be correct that the IA load current would typically lag VBC by 30 degrees if the load is at unity, assuming ABC sequence?
I would say it will lag 30 degree by VA, not VBC. VA and VBC in ideal world, it is lagged by 90 degrees. So probably VBC would be 60 degree difference between IA.
Okay. Next question is for Mohit. If fault current always lags the fault voltage, please explain how could the MTA be advancing the polarizing voltage?
As I explained earlier, fault current can lead the fault voltage as well. So the second part of the question was what did you ask? The MTA? Can you repeat that?
How could the MTA be advancing the polarizing voltage?
Yeah, so the MTA is decided, on base of the polarizing voltage. So it takes polarizing voltage as a reference, and based on that reference quantity, you can have the MTA. Let me go back here. Let me show you really quick. Here is the MTA setting. MTA setting is based on the polarizing quantity. So my MTA setting here is lagging by 60. So that's what it is. So MTA always lags. It looks for polarizing quantity as the reference, and have the numbers based on the reference.
Okay. Here's the next question for you, Mohit. We often use 32 GFR or 32 QFR for MHO element supervision. There are a few instances in which we use a 67 element as well. Is there a benefit either way? I've heard that the 32 method is more sensitive.
Uh, 67, 32 is nothing but your directional power. So 32 is measuring the magnitude, the multiplication of voltage and current, and then decide on the power. So the applications are different for 32 and 67. 32 is looking for directional power, so reverse power applications in generator protection, and then you have those are 32 and 67.
You would?
Mohit,
Unmuted.
Oh, it's a.
Yeah, added to Mohit's question on Mohit answer. Thanks, Mohit. 32GF and 32QF is a direction element. It's like a ground and ground zero sequence and a negative sequence detection in the SCL relays. It's specific to one particular relay. They use a negative sequence element and a zero sequence element to start measuring the 67 functionality. It either can be used, and it's true, yes, 32 is very sensitive. You have to be configured, set properly. Yeah.
All right, the next question is directional overcurrent protection a good application for a transmission ring with multiple sources, generators, and grid connectors at different locations? Since fault currents can flow in any direction, the application of 67 elements seems problematic.
It's a good question. The purpose of 67 is mainly started to protect the parallel lines, to avoid misoperation in the parallel lines on ring systems, because we can protect the sections by implementing the 67. If we time coordinate the 67 elements properly, we may avoid maloperation. It's purely application based, like how we are adopting the relay setting in the ring system and parallel system with the generators online.
Okay. Next question is, are motor starting currents, do motor starting currents affect the directional functionality under normal operating conditions?
It may, but we got a motor direction elements used in the motor production relays, got a blocking option. It's called the speed switch. It is used when you are having motor starting. The speed switches are given for blocking the most of the production functions except differential. So these functions are get blocked till the motor reaches its normal speed or its full power.
All right, and the last question we have is for Mr. Mohit. How can we decide where to use non-directional relay and directional relay?
For radial feeders, non-directional relay has proven its worth, but you have a ring network. It's good to have directional relays. That's the application I've seen.
All right, and it looks like that is the last question that we have. So we'll go ahead and close out the webinar now. Thank you all for attending. If you can please remember to answer the survey as you exit the webinar. The survey also includes a field for you to request a quote or demo if you are interested. Thank you all for attending and have a great weekend.